first speaker is, I think,
I'm Zach
Zach.
Manchester.
Yeah, Zach. And then
Standing in for John Zhang.
Yeah. So yeah, please take away.
Sure. Yeah. So I'm here to talk about really. I guess, is this working? Okay. I'm really here to talk about this work primarily done by my PhD student John Zhang, who couldn't be here, along with a whole bunch of other collaborators between our lab at MIT and a bunch of former lab members and collaborators at RAI. And the project was led by Simon Lickliash, the former lab member who's at RAI now full time. So to kind of kick things off and offer some inspiration for this project, here's some examples from nature of local manipulation where animals are manipulating things that are way heavier and larger than their own bodies. In the case of the dung beetle, that ball is like 50 times the mass of the beetle itself. And in the case of the beaver, they move around branches and chunks of trees that are many times their own body lengths, right? You compare this to what robots can do right now. It's not that impressive, right? Like most of the local manipulation tasks our robots are performing are with lightweight objects, quasi-static tasks, and highly specialized policies where we have to basically retrain a policy from scratch for every new task, right? Compared to these animal examples where heavy objects, highly dynamic, and super general, right? So given that it's 2026 and teleop and behavior cloning are all the rage, I think it's worth kind of thinking about this a little bit. So this is an example from Boston Dynamics where we've seen humanoids manipulate large, heavy objects, do things that are pretty dynamic, right? And this flexible rope being one example. But I think it's a real question still how generalizable these things are, especially when we move past humanoids and look at robots with other morphologies, right? So Spot with the arm here has 5 appendages instead of 4, and teleoping this is way less intuitive. And you can imagine lots of other even weirder robot morphologies. So this was actually teleop successfully, but you'll notice the video is sped up 10 times. So it's not very dynamic. It's really slow. And I think part of that is the morphology gap makes it hard for humans to intuitively control this thing. So how do we do this? I think we're now, in these kind of weirder situations back to our old friends, reinforcement learning and MPC. And I think these are a lot closer related than we might imagine at first glance. They're both solving the same problem, right? Same kind of optimal control problem. And in the case of sample-based MPC, at least, they're both using 0th order optimization to solve this problem. And I think there are actually some really interesting pros, cons, strengths, weaknesses here that are pretty complementary. So in the RL case, you get cheap online inference. You can get very good robustness with domain randomization. But if you go outside the training distribution, performance drops off really rapidly. And it takes a lot of offline compute to train these things. On the other side, on the MPC side, we get good generalization, a lot of runtime flexibility, but we have kind of expensive online compute because we're doing everything online, right? And you suffer from cursive dimensionality. And also for these sample-based methods, they don't do super well with unstable open loop systems. So what Suma does is basically try to get the best of both. We take a low-level tracking policy, that's a reinforcement learning policy, that takes in higher level commands in a lower dimensional input space. So basically torso, pose, and then end effector positions for targeting these manipulation tasks. We basically roll that low level RL policy into the dynamics. And then we do sample-based MPC on top of that in this sort of lower dimensional input space. That low level policy also pre-stabilizes the dynamics so that it makes everything easier for the sample-based MPC controller. And to just be clear how this works, right? We've basically rolled that RL policy into the dynamics that are being used in each of these rollouts for the sample-based MPC controller. And that sample-based MPC controller is sampling from this lower dimensional action space instead of the raw joint space of the robot. So some examples of what you can do with this. Here's some examples of moving around heavy objects. One thing to point out here is the cost functions get really easy to engineer now and really simple compared to what you would need for pure MPC or pure RL. And this becomes super generalizable. This is the same low-level policy with only very small tweaks at runtime to that cost function. And we can now generalize across a whole bunch of different objects. And you can see that the generality we get across objects here is way better than either MPC or RL alone. And as you move away from the object the RL policy was originally trained on, which is that box, the performance really drops off. Similarly, we've got uprighting here of different objects. We're trying to sort of flip these things up. And same story generalizes across a whole bunch of objects with essentially the same policy. And same story here, we get really good generalization with a single low-level RL policy and simple runtime tweaking in the NPC policy, and it dramatically outperforms both RL or NPC on their own. Finally, this does work on humanoids. We've done a bunch of stuff with humanoids in sim at least as well. And I'll leave it at that, and I'm happy to chat at the poster and find more here. And John can really answer your questions because he did all the actual work.
All right, let's thank the speaker again. Because of like we're behind the schedule, we probably skip those questions. We can probably do it offline today. Let's thank the speaker again. And then, yeah. The next speaker is Bing Fang, and he will present learning versatile humanoid. Oh, can you join Zoom? Join Zoom also. Yeah. Sorry. No. So, zoom in. Yeah, share screen. So I will share the screens. Yes. I think that would be great. All right, perfect. Right, yeah. Thanks. So I can start.
So hello everyone, I'm Bimanual from Bimanual University. Here I'm very glad to introduce our work, learning versatile humanoid manipulation with touch streaming. Let me start with fully autonomous place roll demo to show what our system can achieve. The robot must perform wall body motions to maintain stability, while perform a series of manipulation tasks, for example, dragging heavy boxes on the floor, capturing the clutters, precise tool insertion. Opening drawer and cleaning table. And later, catching sponge and wiping the table. So from the videos, we can also see why humanoid manipulation are always so challenging. Because there are three different kind of capabilities you must work together. The whole body stability, touch awareness, and also full hand dexterity. Most current existing work only address part of that combination. So here we're going to introduce Human Touch Gene, HDD, a touch-aware humanoid local manipulation system with an efficient single-stage touch-aware policy training pipeline. First, we utilize a teacher-student framework that trains a lower body controller maintain balance while checking torso orientation, height, base velocity, and diverse emotions. During collaboration and data collection, we mapped human VR motions to torso commands, wrist targets, and also hand targets, while another device will dictate the base velocity. HD takes into visions, perceptions, force, and tactile informations, and action experts will output structured action modalities, and dream experts will predict future tactile lanterns and forces. Well, separate modular action experts will allocate the capacity to any effector, torso, velocity, and hand targets. So small but critical commands will not be overlooked when combined action outputs comes from transformer decoder. In parallel, modular gene experts will predict hand joint force vectors and also future tactile lanterns, so that the shell representations will learn how contact evolve. In the real-world data collection, the robots records man and wrist visions, perceptions, force, and tactile informations across two hands. So why we choose tactile lanterns? Because the raw tactile are sparse, noisy, high-dimensional, and hard to regress. But lantern tactile are compact, semantic, more stable, lower dimensional, and much easier to predict. We learn to predict future tactile latents in a method similar to JAPA, with an exposure moving average target encoder supplies balanced supplies stable supervision without reconstructing raw tactile. We test our systems in 5 different real-world tasks. T-serving demonstrating bimanual locomotion with stable transport. Catalytic scoping focus on low profile to use. You can also see the further recovery from the lab videos. So we can set the lab videos. Power folding. Work organizations. It requires capturing and pushing of the thin objects. And also T insertion. So for our results, we find that adding touch observations does not guarantee improvements. But with modular design and touch streaming, our methods substantially improves the success rate. Meanwhile, in ablation, we also find that predicting future touch helps, especially predicting future tactile lengthens, outperforms predicting raw tactiles. Also, you can see from the videos how predictive finger forces and future tactile lengthens are close to the ground truth, which means touch streaming predicts meaningful representations. Yeah, for fact, we demonstrate our systems for just about 2 months ago. So if you're interested, you can kind of our poster, also scan the QR code. Yeah, that's all. Thank you.
All right, let's thank the speaker.
I'll just stop sharing.
Yep. And next speaker is Jihan Wang from Berkeley, presenting counterfactual video generation for humanoid local manipulation. Hi, Jihan. Could you share the screen? All right,
Yeah,
perfect.
hi, can you see it? Just double checking, can you see it well?
Hmm?
Hello, can you hear me?
Yeah.
Okay, can you see my screen?
Could you start slideshow?
Okay,
All right, it works great. Yeah, you
okay,
can take it.
perfect, yeah. All right, thank you. All right, hi everyone, I'm Zihan. I'm presenting our latest work called counterfactual video generation for humanoid local manipulation. So let's see some results first. So our pipeline is a real to sim to real pipelines that the inputs given a subset of videos. We are learning one single policy that can do a zero-shot sim to real for diverse 27 real-world objects, just purely driven by onboard depth and the root commands. So importantly here, we use 0 real-world training data. That means we do not scan anything, we do not capture anything, we even do not record any real-world videos. We're just purely driven by video data. So all the videos you're seeing here is shown by is the rollout of one single policy that's autonomously with joystick steering. It can do various of objects. So what's the motivation in doing that is robot needs generalization. We human can generalize because we benefit from the rich interaction experience. And the problem is, how do we get this to a humanoid? So robot must first learn how to learn one skill very well across diverse objects. That arises 2 aspects. First is how do we get various assets, and 2, how do we get the pair motion? So this data pyramid told us the data is still a big challenge, and the one possible way to do this is by inferring from web data. However, the bottleneck are weirdly just the RD videos. So despite massive internet video exists, you'll find them very hard to use because they often have undesired motion patterns, suffer from severe occlusion, and also having a lot of weird camera effects and clipping effects. That makes the usable video, which contains clean and full body human motion, carrying everyday objects very limited. So our insight is video model, which pre-trained on large-scale internet videos, already captured the distribution and understands such interaction. We just need to prompt them correctly. We are proposing this called counterfactual video generation is necessarily doing a video-to-video generation. So what this means is we are giving a reference video as the seed video, which is called factual video, or person carrying a box. And what we're doing is we add a very simple counterfactual text prompt, ask it to change the box to something else. For example, change this to a barrel or a lamp. So that's called counterfactual videos. What if I'm carrying a lamp instead of a box? We're generating these counterfactual videos. So doing this actually have several benefits. The first is because we have a reference real video, it actually gives us very realistic lighting and natural motion pattern. And such video model can also give us video prior. So all we need to do is to sample multiple times. It can naturally give us a lot of diverse objects with this pair motion. It's actually being affordance aware because you can see when it's carrying a lamp, it's grasping its stem. And because we have this reference video as reference, the text prompt is very simple and scalable. All we need to do is to ask the model to preserve the background and lighting, which is the realistic parts. We ask it to just replace the box with something else, so we can have a very good quality videos out. So here, let me show you some of the results. So only one video is the seed video, which generates the rest videos by V2V prompting. Actually, you can see it's very good quality. If I don't tell you which video is real, you can barely distinguish from them. And from only its seed videos, our pipeline generates over hundreds of counterfactual videos that contains lots of interaction demonstration of how person handling different objects. So given one single of them, we just do this human object retargeting. And how we do that is we treat contact as the task level invariance for both reconstruction, retargeting, and RL stage. So we use CRISP to initialize the human motion and scene geometry. And for the object parts, we just use SAM3D to initialize the object on the first frame and optimize its pose to fit scene geometry. So everything in the first frame is simulation ready. And we infer the contact events from human and object motions to know when the contact happens. And later we're just anchoring the object pose with human motion when the contact starts and release when the contact ends. And doing this is not enough because we are doing monocular reconstruction. All you need to know is one single view information. So the human joint can go wrong. If we just naively apply previous retargeting methods such as omni targets, which assumes perfect human object data, it will just fail. So we additionally infer that objects should also recognize human joints. So we use the same contact points we derived from last stage to ask the robot and the effector to be at the same position. So we can have a physically plausible interaction compared to previous omni targets. And by doing this, we can have we bridge the gap from this noisy reconstruction to physically plausible robot data. And now our policy can actually learn how to deal with all those diverse objects. So with our pipeline, we can have high quality reconstructed kinematics results. And with all those data, the rest is very simple. We just train with the classic pipeline. We just tracking the robot object target reference and distill them into a depth-based student. We can do a zero-shot symmetry in such way. The only contact reward beyond the pure tracking is ask the end effector get closer to contact points and apply reasonable force. And we compare the two policies we train from different data sources. So first is our Momo that train as which classically used for training such policy. We prove our data, our pipeline can benefit from our data to generalize to diverse unseen objects, both in sim-to-sim and real-world experiments. So let me show more results. So all the video.
Oh, we are out of time. Could you repeat it quickly?
Oh, sure. Just 30 minutes. Okay, so all those videos are rolled out by a single policy, can do very well on never seen in variations of in-domain categories and can generalize very well on the categories you've never seen before. And our policy can do very well on as smaller as the pencil box and can do large as the biggest being we see in the office. And it also be strategy aware. So when it's close, it just goes direct grasping. When it's far away, learns to approach first in different ways and then grasp. And if you place object in different orientation, it can also learn to grasp them together. And when the object is slippery and fall down, it learns to re-grasp. So here is an overview of our method can generalize across 27 diverse objects in just one single policy. Yeah, I will release this work very soon. Thank you.
All right. Thank you very much. Thank you very much, Jian. The next speaker is Changhu, and then introducing Omni Extreme. You can share the screen. All right, works. Take it away.
Yeah, hello everyone, I'm Shang Zhu, and I will introduce our work on Extreme, a framework for high dynamic general control for humanoid robots. This is a joint effort between Big Air and Unitary Robotics. Let's begin. Sorry, there's something wrong with that. Okay. The motivation of this work is to make humanoid robots to have the human-like motion intelligence. In character animation, humanoid characters already can perform a huge variety of full body motions like flips and handstand, which is already very close to human motion capability. And now let's turn to the real world. The Wubo show on Chinese Spring Festival Gala shows amazing robot control accuracy and agility. However, it's mostly trained specifically for certain motion. While works like GMT and try to scale up motion diversity and make progress, it is still far from the diversity and difficulty level of the overfitted policy. In practice, most multi-motion trackers simplify motion control difficulties when the motion diversity increase, just like this curve. The fidelity decrease when the scale increase. And we call this problem the generality barrier. Tracking fidelity and sim-to-real quality decrease as the scale increase. Our goal is to build a scalable controller, maintaining fidelity while scaling to diverse scale, just as this blue curve. And to do this, we compose a set of extreme motion as a test bed to study better learning and better sim-to-real solution. And to answer the question, can one policy handle diverse high dynamic motion under real-world constraint? And our solution is to build a decoupled learning, to build a two-stage pipeline to decouple learning and physical execution. First, we focus on solving the learning problem. If the learning is weak, the policy may fail even in simulation. And after learning is solved, we then address the physical feasibility and sim-to-real transfer. In the first stage, we train many experts policies that overfit different challenging motions. Then we perform distillation on full matching policy to train the unified controller. And finally, we freeze the full matching policy and only train a lightweight residual network with actuation constraint and strong DR. As Suyuan has already covered extensive insights and methodology detail about this, I will not elaborate further. And here I will show some real-world results and demos. Here are the real-world results across 157 real-world trials spanning across 24 distinct dynamic motion. Omni Extreme achieve consistently high success rate across diverse skill categories. And here are the real-world videos. The first one is a Cossack dance motions. It is a continuous alternating squat with leg kicks. And the second one is a five consecutive Webster flip, showing the strong real-world robustness. And the two below are breaking dance motion with rapid contact switch, and the latest one is doing backhand spring when dancing. All right, and here are more real-world video results. And here is the first one is the hand-to-head stand, also with rapid contact switch, and diverse kicking movements, and diverse rolling movements, and also diverse flipping movements. And there is one more part was mentioned is that all the real-world experiment is fully on board on the Unity G1 robot. We use C++ deployment and 1030 acceleration, and with this two tech we can run our flow policy real time. And thank you very much for listening.
Cool. Thanks. Next speaker is Zhu Kao from Berkeley. Here's share screen.
Yeah, sure. So,
Yeah.
Good morning, everybody. I'm here. My name is Joe Tan. I'm here to present our recent work of Tango, humanoid navigation, cloud environments with a whole body visual language action model. Let's start with our motivation. Existing navigation VLA models excel at in the wild scene understanding and trajectory planning. However, their planar action space is fundamentally limited to complex clutter environment traversal, such as this one. So their action space is basically 2D delta XY or delta L, which is unable to handle whole body like humanoid robots to traversal in the clutter environments. And recent real models, such as Psi0, as this one, are proved to be capable of jointly learning whole body motion representation for complex manipulation tasks. This one decouples the upper body and lower body into two control scenarios. And the upper body, they jointly predict the joint poses, and lower body just a high-level command. But with the development of whole body control such as Sonic, it has been making great progress with universal tracker, provide robust motion tracking in the real world. So how about we leverage the idea of whole body VLA models for solving semantically bounded navigation problems in cluttered indoor scenes? So our problem definition is very simple. Given language instruction and RGB image-only observation, the policy learns to predict the whole body action, basically the 29 DOF joint pose plus row pose for cluttered indoor environment navigation. Our trained dataset is totally in simulation, so we deploy this as a zero-shot sim to real case. Our large scenario are basically from some pre-built, very realistic indoor scenes, but we add some augmentation to make sure we have some full obstacles to learn the cluttered avoidance. We got basically three types of obstacles to add. The first one, stride. For example, you're going to make a big stride to cover it, and single basically make a very narrow gate. So we got to like sideways walking, stepping it. And finally, skull, you have to bend over to get over it. And the most tricky part of our model is to generate such motion data. Basically, we have first planning the whole trajectory in 2D. Basically, we use some A-star searching to get through and avoid those unavoidable obstacles. For example, a very big refrigerator of the whole wall, the tall table. You can just go through them through any whole body motions and just avoid it by the 2D path. And then we use self-mimic, adding some virtual force to make the motion really collision avoidance, like you guys bend over through those obstacles and finally track it using Sonic. Here's one example of our data sample in the simulator of ethics scene, basically. You can see we have very realistic rendering. We got all kinds of, sorry, the light is a little bit dark here. And we got all kinds of obstacle avoidance actions during this data sample. And we finally go through the destination described in our problem. So here's our whole pipeline overview. So basically, still a very typical VLA model structure. But there are two things to note. The one thing that we actually got two cameras here, which I'll introduce later in the next page. So we got to train the image token projector here, and we still use a pre-trained VLM backbone. And for the action expert, we use training time RTC, which is called real-time chunking. And this is very similar to Psi0, but here we are actually smoothing the whole body joint pose, just like most VLA, which is most previous VLA models do not do. And finally send it to the sonic tracker and to the robot deployment. Here's the thing, we got two cameras. The one in the top of the head, which is not the unitary default camera. We use this to get a wider field of view and still use the original cam to get a downward specific camera view to look at some obstacles in the ground. And we also have a instruction input, and we use it as a client server to end deployment. And finally, we need to upsample the action chunk to 50 Hertz which is compatible with sonic tracking. Here are some statistical results. Basically tested in the benchmark of navigation. You can see that compared to previous social models, they don't even have low-level trackers or controller. They're basically, theoretically, they can even go through the walls without any collision, which is insane for the real cases. But we, with low-level tracking, are actually outperforming them in most of the metrics. And also on the specifically augmented data set, we can achieve even higher performance compared to previous navigation VLA models with very vanilla-like collision avoidance prior. And we also did some ablation study basically to test if our sum of parts are just introduce some bias for our work. Basically, we tested if we just remove the action first, still downgrade to a 2D case like previous navigation benchmark did. And we also show very strong performance. Finally, due to time limitation, I gotta show you only 3 real-world cases and more demos on the way, and we're expected to be totally open source soon. This one is a very long horizon navigation indoor, and you can see it follows exactly what the prompt says. And since it's 0,0, we don't even have this thing or this specific trajectory in our training data, so it's totally zero-shot generalization in the real world. And this whole action is very smooth. And here we demonstrate some specifically the collision avoidance actions to clearly show it has some specific collision avoidance capability, which is very smooth. Yeah. So that's all, and thank you for listening. Feel free to ask me any questions later. Thank you so much.